What's up, Linear Algebra Bros? It's Mr. C here, taking you through the first part of the Section 4.5 notes. By the way, Section 4.5 is on dimension. Did I mention that already? If not, then here it is. Section 4.5 is on dimension, which by that we mean the dimension of a vector space. So as we'll see, the dimension of a vector space is based on the vector space's corresponding basis. So it's going to be helpful to remind ourselves of what a basis is. A basis is a minimal set of vectors needed to express any arbitrary vector in a vector space. In layman's terms, a basis is a set of vectors that not only spans the vector space, but also is linearly independent. Okay? So I want to remind us of some common bases for certain vector spaces. They're the standard basis vectors, or the standard basis for each of these. For instance, a basis for R2 would consist of the vectors I and j. A basis for R3 would consist of the vectors I, j, and k. A basis for R4, I'm going to abandon ijk notation and now use the e subscript notation. So e sub 1, so that would be the vector 1, 0, 0, 0. E sub 2 would be the vector 0, 1, 0, 0. E sub 3, 0, 0, 1, 0. And then e sub 4, 0, 0, 0, 1. And then, of course, we have a basis for polynomial space. Keep in mind that P sub n stands for the set of all polynomials having a degree less than or equal to n. So if it were like P sub 2, we're looking at all quadratic polynomials. If it were P sub 50, we're looking at all degree 50 polynomials. But either way you slice it, the standard basis for P sub n is a set of monomials, the first being 1, the second being x, the third being x squared, all the way down to the monomial x to the n. Now, these are not the only bases for these vector spaces. As we saw in some of the earlier sections, namely the section on basis, provided that the set spans and is linearly independent, that would be a basis for the vector space as well. So for example, for R2, the vectors I, j aren't the only vectors that span it, nor they're not the only two vectors that are linearly independent. All right. But here's an important result. No matter which basis you use for your vector space, it's going to have the same number of vectors. So that means if I choose another basis for R2, it's going to have two vectors. If I choose a different basis for R3, that's going to have three vectors, so on and so forth. So that brings us to the definition of dimension. The dimension of a finite dimensional vector space V, so something like R2, R3, R4, or P2, P3, P4, so on and so forth. The notation we give it is dim of V. The dimension of a finite dimensional vector space V is equal to the number of basis vectors for V. Well, that kind of begs the question, okay, well, what if I have a vector space consisting of just the zero vector, which those vector spaces do exist? Well, in the case of where you only had the zero vector, that vector space is said to have dimension 0. All right, so with all that out of the way, let's go ahead and see if we can find dim v for each of these vector spaces. So the dimension of R2. So we have some evidence that a basis for R2 is going to have two basis vectors. So the number of basis vectors is equal to 2 for R2, which implies that the dimension of R2 is 2. All right, so in other words, 2 space is 2-dimensional, so hopefully that's not too much of a stretch of the imagination there. R3 has 3 basis vectors, so that means that the dimension of R3 is equal to 3. Alright, so in other words, 3 space is 3-dimensional. Again, nothing too much of a stretch of the imagination there. You can probably see where I'm going with this. The dimension of R4, it will have 4 basis vectors no matter which basis you use. Therefore, the dimension of R4 is 4. Now, the dimension of P sub n is not n, but it is related to n. Let me just scroll back up to show you the basis for Pn. There are actually n plus 1 monomials. That's part of the set here. So what that means is there are n plus 1 basis vectors for Pn, no matter which basis you use. Therefore, the dimension of Pn is n plus 1. Alright, so that's it for this video. In the next video, I'll discuss the theorem that's at the bottom of page 1. In the meantime, let me know if you have any questions about this one. Otherwise, I'll catch you in the next video. Thank you.